Good. First of all, thanks everyone for coming. Yeah, so this is the second short course for the radar meteorology or the radar field experiments. Yeah, will be given by Professor Yu. Okay. So all the Zoom short courses will be recorded, and so you can review it when you go home. Okay. And another announcement. So for the radar demo, we have to postpone it to tomorrow morning because it's raining outside. Yeah, so instead the radar card will be out to collect the data. Yeah, hopefully we can share the live data visualization with you. Yeah, for the radar data. Okay.
Okay, thank you. Barry, thank you for the introduction. So what I'm going to talk about today in this particular class for about 15 minutes or so is going to give you some radar background. You already heard, maybe, or some of you already heard some of the radar scanning strategy, this and that, but I'm going to kind of step back, looking at radar from a little bit from radar engineering side. Okay, so don't be scared, and it's not going to be anything deeper. And all you need is some common physics background. That's all. But before that, before I even talk about radar, and some of you probably know what radar is, but I do want to show you this particular video. Actually, was made by a National Science Foundation. Hopefully, you guys still have the sound too. So it's a very interesting. We'll see how that goes. Okay, I'm just going to stop right here. And what did you guys hear, or what did you guys see in this very short video? Anything? So now I'm going to share my screen again.
I thought it was interesting that the bat was able to directionally focus where its voice was going to be able to directly aim it towards the target.
Very good. I mean, anybody else? So I think when you look at how bad it's going to locate a target, then I don't know if you hear that the chirping sound actually different, right? So when we call kind of at the beginning, we call it kind of surveillance mode, that chirping is kind of long and short. And basically you try to surveil what's going on. But once you say, hey, there's the particle direction, maybe there's something over there, you will see the frequency the chirping become more and more rapid. And finally become really rapid, you know that's the direction where he actually attack or get the insect. So this is, even though the bats basically use I think the sonic beams that I think from his nose that is transmit this particular sonic energy, but the radar work in a very, very similar way. You kind of have just doing things in a different way of thinking that instead of the sonic energy, the sound waves, radar basically use electromagnetic waves. So everything else is pretty much similar, but the way that the bat is able to capture this particular insect by changing the chirping, I can say in military radar, they do that, but honestly, in weather radar, we don't. We are even not up to the bat standard yet. We just send out the same thing again and again and again. There's the depthness to what's going on in the environment that's very, very minimal, but that's an open research topic that people start looking at the possibility, because radar is definitely capable of doing so, but how are you going to feed the information collected by the radar to drive how radar is going to run in the next step? That's a big research question, because everybody wants different things, for example, if you do the forecasting, you want the higher level, you want to see everything, right? If you do other application, you want to see different things, different update time, and so on and so forth. So when you adapt, and adapt to whom, that becomes another kind of big question. So anyway, I'm not going to talk about all this deep stuff, but here's really want to talk about something about the fundamental and some that you probably know, and I present some of the few slides. You probably have seen that if you participate in this virtual student workshop. But here I'm just going to go through these kind of briefly. And what is radar, what radar can do, and I think everybody should know radar is nothing but the name itself is the acronym. That the acronym itself specifically tell you what radar does. So it means the radar itself goes to radio detection and ranging. Basically, radar does two things. This is a kind of the very basic radar when it was developed. It does two things, two jobs. The first one is detect the target, and the second one is ranging. So I kind of used the way that when I said target in our context, of course, that means weather radar, weather, right? So specifically, there are different type of precipitation, but at the same time, don't forget that we are not just seeing just the weather, we see other things too, like airplanes, we can see it, insects, bats, and all these birds, we can see that too. So, but the target that we want from weather radar person point of view, we want weather only. Other things we either call interference, clutter, noise, those are things we try to get rid of. Okay, so going a little bit deeper about what radar can do, or what is radar, it is instead of just what it does here, just talking about a little bit more about the system. It's the electromagnetic system. Like I said, radar uses electromagnetic waves to send out the energy to get the information. It's basically remote sensor and find out detection and the location. Means radar is runs in the native coordinates, a spherical coordinate system. That means the location means in the range as in elevation. The radar is able to detect the target of that specific location. So here is pretty much to emphasize what kind of the target. Well, I kind of use this word target because I won't present in more genetic form. That from military point of view, they say they are interested in a point target, like a missiles, airplanes, and those are things for them. It's called point target. And for weather radar, we look at weather, we call distributed target. That means the things typically much larger in space, extended, in kilometers, and larger than what typically the radar resolution can see. That's what we call it. It's a distributed target. So why radar? Well, before that, you probably want to ask yourself, what other options I have before you make a decision about radar, right? So in terms of sensing the atmosphere, can you think about anything else other than just radar? Yes.
Maybe weather balloons.
Weather balloons, those are in situ measurement, right? You actually measure that you balloon carry a sensor. But yeah, I want to think about remote sensing. It's satellites, right? So what kind of instrument do you think satellite can carry other than radar? Radar can be carried by satellite too. Yes, so that means the optical sensor, right? So anything else? So there's one more. So that's three typical types. So you do have radar using electromagnetic waves, and the other one use laser was optical, right? So there's another one. What bat use? So there's something called sonar. It uses sound waves. Okay, so then each instrument they have their pros and cons, right? So not I'm a radar person, but I will not say radar can do it all. But the radar has its limitation. It also has its benefits. The biggest benefit of radar is can operate day and nights, and also in all weather conditions. So I kind of have to put an asterisk right here. So when you say all weather condition, really depends on the wavelengths of the radar. Sometimes when you use a high frequency radar, you cannot quite penetrate the weather. So you can see So that's kind of the key. So the potential radar or the possible radar application here, I just want to give you kind of daily things or some of the daily things. Probably see the police use the radar guns to measure speed of your cars and everybody's car. Then probably when you play baseball, they measure speed of the baseball. So those are use radar because radar can measure this particular speed. We call radial velocity of the target. Of course, and more you can see those fancy cars, they have a radar detection, try to help with either the autopilot or other automotive radar applications. And of course, the most common things is using for the military, missile control and the guided missile and so on and so forth. So this is for the air surveillance. If you're at the airport, you probably see these red stuff. This is the air surveillance radar. I see that at the airport. Some airport you also will see a weather radar too. And this is one of the weather radar that we built that at OU a long time ago. And the sad part, it was destroyed by light, which is a really embarrassing experience. But that's kind of tell you that radar that we have these fancy electronics, but if you don't do lightning protection carefully, it got destroyed. So he got hit by lightning the same day twice and kind of burned out everything. When we went in there, everything, all the radar were charred and the electronics was burned out and it's disaster. So, but at least we got a few years and good life out of it. So now it's we kind of tore down all the radar and resell some of the components into the company. So some of those stuff. So more interesting, probably some of you don't know because radar can detect really. We talk about can detect the speed, right? But you also can detect some kind of vibration in a way that's kind of speed. So you can actually detect people's heartbeat. So that's become a rescue tool that when you this is one I think Nepal, there's a big earthquake. So NASA brought this kind of handheld radar system going there, try to find survivors. Then they try to find a location that the radar can go through the degrees and find out there's a heartbeat. So that'll be the location they want to dig first. It's kind of similarly, there's also another thing to ground penetrating radar. Radar does not only look at from the atmosphere only. You can also penetrate ground, not very far, but you can penetrate ground to a certain level to detect that pipes and you have to make sure the pipe is working properly and so on and so forth. So here is some very brief, very simple we call block diagram that basically tell you the functionality of a radar. So the whole thing here is basically a very simple way to describe a subsystem of a radar. So I'm just going to go through these very quickly, kind of give you some idea. So for example, radar just like that bat, you basically, if you think of that, you send out the sounding things, right? So it's not you don't hear it, it's actually sending out a pulse, right? Inside a pulse actually has a different frequency modulation for or chirping. Okay, so radar does that too. So instead of sending one, so when you send out this, sending out this sonic energy, radar send out electromagnetic energy, turns out waves. Okay, so and the transmitter is basically does that. It generates a particular we call waveform, or you can think about that chirping of the bat. It's making how that bat is. But at the same time, when we generate that signal, typically it's very tiny because it's easy to control. But for you actually send out to the atmosphere, we send out very, very large power. So just give you some ideas of this next red that what you see typically from Weather Channel, these big radars, you send the power is about 750 kilowatts. So just some idea that your light bulb is 100 watts, right? So that's pretty strong. So that send out 750 kilowatts. And the radar I show you that from OU that they send out 1 megawatts power. So some of these radar they're very, very powerful because what you're seeing is not really the reflection signal. You see, you're receiving those we call backscattering signal. That's very, very tiny portion of the signal is sent out that coming back to your radar that you receive. So that's why you want to send out a lot of power illuminate there when you receive actually a little bit. Okay, so that's basically what transmit does. Once you generate the waveform, the jumping that you want, you amplify to the power level that you need, then you go through an antenna, then kind of broadcast the signal out. So you can try to think about the antenna is that it's a way to focus your energy to a specific location. the way we can try to think about, so we talked about earlier, radar can detect or determine the location of the target. The location, there are three things, two in the angular direction, right? One in the range direction, the spherical coordinate system. So in order to determine the angular location, just like if I have you can think about if I have just one light bulb and you illuminate all the location, then if you have one received signal, you really don't know where that location is. So what radar does is instead of illuminate all direction all over the place, it sends out very, very narrow beam, like a flashlight, very concentrate energy in the specific location. Then it actually rotates around, like you guys saw this morning, it rotates around, at the same time record the location of where the energy is going to and coming back to. So therefore, when you look at your data, you say, hey, here's echo, here's echo, you know the location. So in order to determine location, you typically you need a very narrow beam. And the antenna does that. You kind of concentrate your energy to a particular location. So another example, you can think about back in when you were young, I don't know if you play around with the magnifying glasses, you try to burn maybe tissue or try to burn some insects, or you kind of doing this, right? You try to focus your light into a very tiny spot. This is the function of antenna, right? You focus all the energy coming to that magnified glass and then focus that to a very, very tiny spot in that location. So that's what the antenna does in terms of transmission. So once the energy goes out, then it propagates in the space. Once it hits target, partial of the signal, like we talked about, fast scatter back to your antenna, and very, very little. So the ratio between the transmit power and receive power, they can be on the order of 10 to the 10s or 20 to the 12s. So that's a big ratio. So coming back a little bit, then going back to the receiver. So the receiver, the main idea about receiver, like we talked about, the return signal is very small, and the receiver basically kind of maximize the signal that you want, at the same time suppress the noise that you don't want. So in a way, you can try to think about what we call signal to noise ratio, and the receiver try to maximize that. So once you have that, in the later part, it becomes different application. You have different kind of the signal processor. Then process the signal, process the information that you need. We'll talk a little bit more about signal flow later. Then basically the display. So there are two basic information that here I want to introduce the radar can measure. So we talked about early on, the first thing radar can detect called range, means the distance from, for example, from here to the wall, and what is the distance. So the distance, the idea is basically this is what I call time delay times speed of light. The radar waves propagate the speed of light. And the time delay is like this. So the example I want to use is that this is too short, but that's some significant distance that I want to measure. I don't have a radar, I don't have any instrument. What I can do in a very poor man approach is I can time my clip, right? The clip will hit the wall and coming back there. If I can make up the time, how long does it take for my clip go to that target or wall, then come back, right? I can kind of estimate the distance from me to the wall. Does that make sense, right? So that time delay, that we call the time for my clip from me to transfer, propagate to the wall, then come back. That's this time delay. Then this time, in this case, of course, times the speed of the sound. But this one, because there are two ways, the actual distance of the wall is half. So it's the same concept, but radar just basically use electromagnetic waves. So the key is that you need to make that clear, right? For radar, the way to make that clear is send out this pulse, just like the bat. Send out that particular energy inside. It's not continuous. You just have that pulse. Okay, so the other thing is radar can measure is something called the Doppler effect. You've probably seen this before. The Doppler effect is if you right here, let's say there's a moving target. Let's say this is an example that a train with a blowing horn coming forward to you. You've probably been asked this question back in the day, and you will hear the frequency increase, right? So this the line, the circle, actually the wavefront. You can see the distance between the wavefront become closer and closer if the target moving toward you, means the frequency increase. At the same time, if you're on the back and the distance between wavefront, all the wavefronts become larger and larger, that means the frequency goes down. So that's what the motion of the target that relate to the speed of the target. Okay, so And the change also that the motion relate to the frequency change that radar can measure. So radar can also use that one to refer or to estimate the velocity of the target. So when I say velocity here, I do want to emphasize we are not measuring. Let's say you have a target moving this direction. Now you are not able to, without any fancy technique, you are not able to measure the full velocity of the target. What you can measure from the radar is by measuring the projection of the target into where the radar is pointing. This one we call radial velocity. We use VR, and this VR is related to the Doppler frequency shift that can be measured by the radar and what the radar wavelength is using. So that's kind of basic idea. The range is based on the time delay, and the velocity, radial velocity specifically, is based on measured by the Doppler frequency effect. So which also means that I don't know how many of you have ever got a speeding ticket.
Yeah.
Not yet. Okay, good for you. I got a couple. So when you see this police car, when they try to get your speeding ticket, you will see they will either very far waiting for you to come into them, they try to measure, or they're on your back when you left, they try to measure. They will never ever try to measure when you're getting close. So why is that? Because if you look at this particular velocity, if the velocity is totally perpendicular to the beam direction, can you imagine what's the radial velocity? Zero. No matter how fast you move, it's going to zero. So if the police try to measure directly passing him, you will never ever be speeding. So you will be fine. Okay, so they will never do that. So, but if you along the way, it's either going toward to him or away from that, whatever he measures will be your speed. So that's what their principle of operation. So I don't know, maybe next time you can try to make a sharp turn or something, make it perpendicular, then I'm joking. So don't do that, it's dangerous. Okay, so that's the idea of radial velocity. So sometimes in the weather, observation, you see zero velocity line. That sometimes doesn't mean that the target or the weather is not moving in that portion of the space. It can be mean that the direction just happened to be perpendicular to the beam. So there are two options. It's hard to tell. Okay, so then kind of going back to, a little bit about the observation of atmosphere. I think some of you answered this question. Maybe I should show this a little bit earlier. And this is my interpretation of all the different instrumentation. So I like to divide the way to measure atmosphere into two ways. That one is the institute, the other one is remote sensing. The way of institute is actually take the instrument to the location, you directly measure whatever that is. For example, temperature, humidity, pressure, these kind of things. Those called institute measurement. Then remote sensing, on the other hand, you don't go, but instead of you send out certain energy that can be radar, use electromagnetic energy, use LiDAR, use solar, use different medium, that different type of energy, then you actually get some signal back. Then you estimate what's out there. You don't directly measure that. So you can think about the institute measurements. Of course, the benefit of that is direct measurement. There's no question about it. You measure them, except that you have a device has some bias. So if that's not the case, you measure temperature 10 degrees, that's 10 degrees, so nobody will question it, right? So, but if you use radar to measure anything, it's a remote sensing. So there's some uncertainty in there. Right. It also depends how good you calibrate your system. It's not going to be a direct measurement. But the good part about remote sensing, for example, for radar, and somebody just mentioned balloon, right? How often you launch balloons? Not very often, twice a day for the operational side. When I did my field campaign, I sometimes do 2 hours, but that's sometimes even that's 2 hours. But the radar can surveil, even the slower radar like operation, they can surveil the atmosphere, within 4 or 5 minutes. They can continue doing that. But in-situ measurement is hard. Let's say if you even go to a higher atmosphere, let's say ionosphere, you want to launch a rocket, I mean, you probably do that twice a year. So instead of that, so it's a very, very different goals. And if you go to the institute, of course, they can have a different platform that can allow you to carry those sensors. You can put on the balloon, like you just mentioned. You can put on an airplane too. Of course, you can put on now become more and more popular. You put on UAVs that they can carry those sensors up and down and go into different storms and try to sample those atmosphere. So here, of course, then we kind of briefly talk about that radar has the benefit of operating day and night. So now kind of concentrate, since this is radar class, right here, we concentrate on radar. But here I'm going to broaden that a little bit. That it's still weather radar in a way, but I'm going to say it's an atmospheric radar. So that including not just the weather radar. So it's a little bit bigger. So there in the atmospheric radar means use a radar that mainly for observed atmosphere. Okay, the Earth. And they're kind of into their three different types. And they have a different operational mode. The first one called wave profiler and weather radar and cloud radar. So here I kind of list their major differences. The first one is the frequency, how they operate. So wave profiler typically is much lower frequency, and weather radar in these three categories kind of in the middle. And you probably 3 gigahertz and 5 gigahertz and 10 gigahertz and so on and so forth. And the other one is cloud radar is much higher. So one example I always like to do that with the class is I came from a science background. I got my bachelor and master kind of in the space science and the atmospheric sciences. Then I moved to engineering for my PhD. So I always kind of hear both sides in a way that always say the other side is easier, right? So engineers say if you do well in engineer, then the physics is not a problem. The physicists say if you know the theory, the engineer just practical things, you can do it, so no problem. So they kind of doing these kind of things. But anyway, so my point I want to make is that they also it's the same thing, but they speak sometimes they speak different languages, even for the radar, right? So for engineers, they like use frequencies, 2 gigahertz, 5 gigahertz, and 10, and this and that. But you know, from meteorologists and from a lot of scientists, instead they like to talk about wavelengths. So this will be 10 centimeter, 3 centimeter, 5 centimeter, and so on and so forth. So it's a different language. So the wind profiler here, I'm going to say is basically it's a much lower frequency, means typically it's much larger. It does not spin around. It's just sitting on the ground. You look vertically. Sometimes you do several things, steering, try to get a wind. So you measure, give you the wind profile, like the name indicates, just above the radar system. Okay, and the weather radar, on the other hand, it kind of does not really care what. I should say it operates like this, so it point horizontally most of the time, then do this PPI scan. So you just go around, the elevator, and go around. Then try to get the storm motion and precipitation intensity, information like that. Now, of course, the cloud radars, of course, then now you start with the vertical pointing, try to look at the cloud, and later on, the roads, especially recently, do the scanning too. But can you kind of guess why the different frequencies, and do you know how different frequencies relate to what you're going to see? Yes.
So it's that the wave for how often, how short or how long the wave is will affect how far it can penetrate into it. So
Yes.
something like wind would be better with a faster wavelength and something that you can penetrate into,
Yes.
stronger.
Okay. In terms of penetration, anything else? So let me ask you this. So in terms of the target size, which one can see smaller size? Can you think about all this? So of course, the higher frequency means the smaller the wavelengths, these opposite related. So if I want to see very, very tiny drops, do you think I should use profiler or use cloud radar? Cloud radar. So it's the frequency basically, all you can think about wavelengths. The smaller the wavelengths, the smaller the particle you're able to see. Okay, so those are very, very tiny. If you want to see really ice crystals in the clouds, those kind of radars cannot really see it. But let's say if you go down, so this one typically you want to see what a cloud evolution, pre-storm condition, those will be ideal. So once you start to become precipitation and start dropping, even snow, hail, all this stuff, then you're going to use weather radar. So even though if you even lower the frequency or the higher the wavelengths, you don't see much precipitation anymore. You start seeing the we call turbulence, especially the clear turbulence. You see bright scattering. So you probably in the airline, if you the airplane, sometimes there's turbulence. Those kind of things very, very hard to see, but those profiles, because the longer wavelengths is much easier to detect those. So just give you some idea about how you can prop the atmosphere. So here, just give you some examples of the profiler. So profiler, there are kind of two different types in a way, based on the size. The first type here, I'm showing you, those are the big profiles, really, really big. So this is one profile system in Japan. So this is about 100 meters across. So the diameter, so those are it was built in the valley. So you probably, this one recently retired. This is a radar in the Arecibo, radar in Puerto Rico. So this one, this is a big dish antenna. It was buried in the big valley. So the size here is 300 meters. So this is huge. This one, all these radar can see very far. And this one is in, I think, Taiwan. And this one is in Peru. This is one of the earliest radar systems. We went there to visit, maybe, I think that now it's probably 6-7 years ago. They have 2 llamas there. So one of our colleagues just play with the llama. So those are big systems, and they can see very, very far, all the way to ionosphere, up to what we call F region. So that's about 500 kilometers or so. Can you imagine how far it is? So they can see very far. In some systems, for example, this one probably cannot see very far, maybe a little bit about 100 kilometers in height. So those are vertical pointing. So there also the other type, this is more related to weather observation. So those are called a boundary profiler, boundary layer profiler. So those are typically a little bit smaller and does not see very far. If the powerful one can see you can see the height. So probably see all the way up to tropopause. Sometimes if you have a storm that can extend it, you might be able to see a bit higher. But mainly focus on the lower part of the atmosphere from the boundary layer all the way to maybe tropopause. So that's kind of the profile system. And this one interesting also, those kind of specific thing called the RAS, radio acoustic sounding system, help radar to detect the temperature of the atmosphere. So this is, of course, those are the weather radar. So for radar, when tomorrow you go out to see, I'm going to show you this radar tomorrow. Honestly, for most of the radar system, the most eye-attracting, eye-opening part is the antenna. And they have all sorts of different antenna that look cool. But if not, and most radar, this is an X-ray, this is OU-prime, they all look similar. It's just a white radar, sometimes different color, because radon cover, all the electronics will be inside. But those are different type of system. You can see those are the S-band large systems, C-band and X-band. So then like I mentioned, so the higher the frequency, typically the size becomes smaller. Okay, so that's why when you want to have a mobile radar system, typically it's on the X-band or smaller. The largest one we have is on C-band. So just here, I want to give some brief summary. This is my personal view of the kind of the milestone in the weather radar development here in the US. And this is the first kind of the radar development. At that point of time, so in the radar development is actually first of all, you only detect the intensity of the storm, nothing else. You don't have even the velocity, that the Doppler effect. You don't have that. Much later, that you start have the Doppler effect inside there. So this is the first Doppler radar. It's a X-band radar that was instrumented by the National Space Laboratory at that time. So that time, and the cool part is that you can see that this is the first tornado detect by the weather radar of also the real-time display. Then personally, I think that the groundbreaking is actually moving from the black and white display to the color display. That changed things, especially impact forecast tremendously, how you can see things differently from the black and white to the color one. And of course, more recently, that another evolution for the breakthrough is used the dual polarization. That by transmit different polarization, that you can get a lot more information. And you probably won't ask what's next. So this was done probably 2014. That's they start earlier and complete the whole national network and upgrade to dual polarization in 2014. So what we're doing now is that we think the next step will be the so-called phased array technology that open up and kind of another dimension of what radar can do. So remember, I talked about the current weather radar system not even comparable to bat that changed the chirping. So the phased array actually has that kind of capability can open up a lot of flexibility how we can spell, how we can detect different type of the storms. So that I think that's the next evolution of the radar. So here I just want to kind of coming back and talk and more focus a bit more about weather radar. Then we kind of have seen something like this. This is exactly the same block diagram like I mentioned earlier. But here just use the graphic got up on this website. And the key here I just want to make is really send out this the wavefront, right? Those are the energy getting on the propagation. And here this is a zoom in version of that. Those waves hitting those little particles or the precipitation, and part of the energy, or very, very small part of the energy will be reflected back and received by the radar. When I say received by radar, being collected by the radar antenna specifically. Okay. Then the next one is, some of you probably seen this before, is the introduction of the parametric or dual polarization techniques or technology. The main reason for that is that, so first you have to understand what is polarization. It's a way to describe the change of the electric field in space. So if your electric field change in space like this, in a horizontal direction, so like this, the wave propagation is like this. This is called horizontally polarized. So you're looking at the electric field. Okay, so if the electric field going like this in the vertical, then they change in the vertical direction, that means it's vertical polarized. So that's kind of what the horizontal and the vertical polarization, that's what that is, electric field. And the reason you want to have that is mainly because the shape of the drops. So you probably know this, better than I do, that the smaller drop, they tend to be a spherical shape, right? But when it becomes larger and larger, it becomes like this. So you can kind of guess, if I just have one water drop shaped like this, if my wave is polarized this way and polarized this way, which polarization do you think can give me more return? Horizontal or vertical? Horizontal, right? Because this one has more intersection, can intersect more of the energy that polarizes this way compared to this way. If it's spherical, then you'll know it's the same thing. Okay, so that's kind of very, very intuitive and basic idea why you want to use dual polarization, because it tells you about the shape information of the hydrometeors. When shape spherical, tend to be smaller, or they be a blade, and of course you have some random shape. So would the bigger thing send out would be like two different? And that's a very good question. So there are different ways of doing that. Okay, so I can send out one beam doing vertical, then the next beam, the same location. So remember we send out pulse, right? So the first pulse is horizontally, then the next one become vertical. So that's one way of doing it. Or more, now the operational radar we send them both. These are vectors. So if a vector going horizontally, a vector going vertically, what's the sum of these two vectors? So it means it's 45 degrees. So they actually send out 45-degree polarized, linear polarized wave going there, going out. When you signal coming back, then you split that into horizontal and vertical. So that's what we call simultaneous transmission and receiving. So that you send out at the same time. So some things where I start looking at, we start looking at some of the circular polarization, that kind of going back to the day, how we can do things differently. So can you guys remind me how much time I have? 7 minutes, okay. I'll try to zip through some of this. So I'm just going through very quickly then why you need a dual polarization. That's probably in the Dr. Barry Wen's class that you probably learn a lot more than she has this radar and satellite meteorology class 4410, right?
Yes.
Okay, so if you want to learn more, please attend this class. But here I just want to give you some very, very high level. Why do we need dual pole? So what's the benefit of that? So the first one is by sending out these two different polarizations that, like I just kind of briefly mentioned, you get some information of different shape of your target or hydrometeors. That you can even go into deeper than that. You are able to do a data quality control and also do the hydrometeor classification. So here are just some examples of if you have a reflectivity. We'll talk a little bit more about this if I have time. This is differential reflectivity and correlation coefficient. So I think I have one example. So here is that you are able to look at those geopolarization radar product and kind of mix them together using the artificial intelligence algorithm. You are able to know those return, are they coming from gravel or dry snow or wet snow or a mixture, or it's a heavy rain, light rain, it's clutter, and all these different type of scanners. So this is called classification. So you are able to use the geopolarization radar product to classify. So for example, you see this strong reflectivity part for this particular case, it's coming from hail, melting hail that in this particular case. And the other part, that's probably one of the most important driver for the geopol is about the improvement of the quantitative precipitation estimation. That with the geopolarization, that you know better about the composition and the shape of your hydrometeors, that you are able to get a better idea about the rain rate and so on and so forth. And the other part that is also interesting, this is the same event observed by two different frequencies. So the one is the S band, this is a 10 centimeter, and this event is 5 centimeter data. So what you can see, this is the same event, but you can see the color here is very different. So the radar is albino. So one thing that kind of drawback when you go into the higher frequency, right? This is 3 gigahertz to 5 gigahertz, is that everything becomes smaller, you can make it more powerful, everything looks very nice. But one thing for radar observation is the attenuation. So the higher up the frequency you go, the more attenuation you're going to suffer. So this is kind of an example that for the S band is a lower frequency, you can see through the stone very well. But for this particular case, that the radar here is actually when you go through this particular strong storms, and on the back of the storm, you have a strong attenuation, you won't be able to see that very clearly. Okay, so this can be a problem because if you don't realize that sometimes if you use a high frequency, you see nothing on the back. It's not necessary there's no storm, it's just because the energy being dissipated, you won't be able to see anything beyond that. They may still have a very strong storm, just not able to see it. But by doing this geopolarization, there's some attenuation correction algorithm that you can use and allow you to use such that even the C-band that kind of getting back to what the anchor signal should look like before the attenuation. Then you can kind of compare with the S-band data, which I would typically assume is either none or very, very little attenuation. Okay, so the other part is from more operational side, they can use geopolarization data that can give you a better forecast skill. So I'm just going to say this very quickly. You don't have to go in there. So this is a little bit more detailed block diagram of what we just showed earlier. So those are the transmit part, and this is antenna part. So all this is basically the receiving part. To break down a little bit more to the margin system, the key part is this digital receiver. But anyway, so don't need to worry about it. So I think some of you who was not in this morning's show course. So some of you were not there. So, okay, now I'm just gonna briefly help through. So in terms of radar operation, there are two ways for weather radar to operate. So this is for a conventional side, okay, even not from operational side. So the radar can do, like I said, this is called PPI, plane position indicator scan. So you basically fix one elevation angle, you go around 360 degrees, then you elevate it, go around 360 degrees. That's this particular type of scan. Okay, that can cover a volume, and they talk about also the tone of silence. So the typical scan from one PPI, you can look at is the radar going around, and this is what the reflectivity, what the velocity will look like. So, and you probably will know which one. If I look at this thing like this, let's say 1D. So you have to know all this location, the Z, the height is actually all different. Does that make sense? Because you feel, even you assume the Earth is flat. If I have been going like this, so when I very close to the radar, the height is very little. When I go really far, the height, what you can see is actually elevated. So you can overshoot the storm. So make things even worse, the Earth is not flat, right? So it's actually curved out like this. So at the really far side, you can overshoot the storm, you won't be able to see of the storm. If you have a very large radar, because the distance we're talking about, this is for this should be for, right, no, I'm sorry, the moving price. So this one is about $100. So for the next ride, you can see all the way to 460. Yes.
When you have those next gen radars, there's like the parts that we see is incorrect for like that.
The height?
Or, okay.
No, what you see, no, you just see exactly what that is. So if you see this one PPI scan, or if you have the radar scope, when you see that, it's just whatever the height. So they don't correct for that.
The notification directional antenna, so it can't stand outwards. If there's no line of sight, it can't.
Yeah. So, well, this is maybe engineering correct. How can you overcome that problem?
More intense.
Yes, you have more radars, right? So you don't have to see very far. The one way to defeat the Earth's curvature problem is that you don't if you have the radar don't see that far, then you don't have that. But you still want to have the coverage. Then instead of 168 radars, now you probably have to have 10,000 radars. So that's another. There's actually another project that proposed something like that. Then you don't need to have this big, giant $10 million radar. You can build something much cheaper. So people already proposed that, and that's another way to overcome that. Of course, then you can look at the research side. They start looking at optimization. Maybe you have a combination of both. You don't have to have one or the other, right? You can be the both. So all these kind of interesting things. So the other one is called RaXPol. So this is, you can see the radar is fixed at one azimuth direction and go up and down like this. And this is what it sees. So the display here, you see this is the range and going up and down like this. Okay, so this is called RaXPol, range time indicator. So let me just kind of, I think my time's up. So there's maybe I'll stop right here, then we can go deeper maybe in the future. So here, I just want to throw out the terminology here. So when you talk to people, at least you know what they're referring to. So for the dual polarization radar, you have two different channels. These horizontal channel needs to receive signal. They split into horizontal channel and B channel. They're supposed to be identical, but of course, in reality, they won't. They should be close enough. And the so-called level 1 data here, those are level 1, level 2, level 3. Those are the next rad, terminology. So for us, sometimes we call those are the IQ data. And whenever you say IQ, those are the raw data. It's the time series data from each gate. So when you process the IQ data, you can get the so-called we call level 2, and some people call the base data. That including two parts. The first one called spectral moments that give you the reflectivity, radial velocity, and spectral moment. And the other part is called dual pole variable. Now you start processing the difference, these two time IQ data. You get a differential reflectivity, correlation coefficient, and the differential phase. Okay, so then once you have those kind of the base data, that's the display that you typically see. And one they can feed that into all sorts of different algorithms. That's such that you get a run rate, you get a hypermedia classification, you get detection, you can get microburst detection, gas front detection, tornado detection, all this different stuff. So they all kind of operate on this. So those are the kind of general signal flow from the very beginning, from level 1, level 2, level 3. Okay. So because in the interest of time, I just have a few slides later, kind of going to describe physically what those are, but I don't think I have time to go through this. But what I can do, I will make my slides available, and I'll send to Dr. Wang, and she can share with everybody who is interested. Then also share my contact information if you're interested. That you can contact me or invite me back next time. Okay. All right. Okay. Thank you very much.